Hello everybody, Adam Lusick here, and today we're going to be talking about the special reinforcement learning algorithm that the DeepSeek team used to train DeepSeek-R1. That is Group Relative Policy Optimization. While reasoning in large language models is nothing new, the DeepSeek team is the first lab to actually fully open source their entire pipeline for how they were able to teach a language model to produce long chains of thought and different reasoning capabilities. This allows a language model to do things like backtrack, consider different approaches to problems, and even reconsider what steps are being taken before finally answering with its final solution to some problem. Which, as we've seen with the release of things like O3's benchmark, as you allow a language model to spend more test time compute, really generating and reasoning through and considering a problem before answering it, it tends to perform much more highly on these standardized benchmarks. As such, this technique provides a way to actually really boost the performance of a language model without just raw scaling of parameter size. And well, for the last few months, most of what we've known about teaching reasoning to language models has been highly speculative and theoretical, as the different closed and private labs like OpenAI have been very secretive about their different processes. We now have a playbook of exactly how someone might be able to do this with the release of DeepSeek-R1's paper. So what we're going to go over today is a dive into how the reinforcement learning algorithm that they used to unlock this reasoning capability works, how the DeepSeek-R1 model was actually made, and then also applying GRPO to create our own fine-tuned open source reasoning model. So let's get into how GRPO actually works. The first surprising fact about it is that this algorithm has actually been around for a while. This was also introduced by DeepSeek about a year ago in April, and it came about as part of their different experimentations with reinforcement learning fine-tuning for math. In this paper, as they're teaching language models to reason through math problems, they found a way of modifying an already existing reinforcement learning algorithm, proximal policy optimization, in a bit of a special way to enhance the learned reasoning capabilities across these problems. I'm only going to cover how proximal policy optimization works at a high level in conjunction with GRPO, but if you're interested in getting a lot more details, you can check out my other video where I use PPO to teach a neural network to play Pong. But at a higher level, the way that PPO works for reinforcement learning for language models tends to follow a little bit of this process. You're going to start with a policy model. And the policy model in this case is going to be the language model that's being fine-tuned. A policy in reinforcement learning tends to be the different actions that some sort of agent is going to be taking, but in our case, this essentially means the behavior of the language model. Then, for a given training example, that's ran through the language model, and then we get an output. That output is then processed in three different ways. The first most important one is of course going to be the reward calculated from that output. Generally at this stage, especially for techniques like reinforcement learning from human feedback, you'd usually use a separate scoring model or classifying model that has been trained on recognizing and scoring what kind of human preference-based output is, and taking the output from the language model is able to provide a score as to whether or not that would align with the different human values that we expect. The output also then goes through a reference model. This reference model is useful in a multitude of ways, but generally what it is actually the policy model, or the language model being fine-tuned, but actually frozen and not being fine-tuned at all. What we're able to do then is use this base model along with the one being fine-tuned as a reference for how much the model is going to change based on the output of the given training example. Through considering these differences, we can calculate what's called a KL penalty. And we use this value to essentially make sure that the updates that we're doing to our policy model being trained aren't so significant that they completely deviate from what we started with. This allows us to maintain a lot of the prior learned behavior that we already have gone through when creating or doing other fine-tuning runs on the language model. And then the third model that this output is ran through is going to be what's called a value model, which is essentially going to try and predict the expected future reward from that output. Then taking the expected future reward and comparing it against the actual reward that you were getting, you get what's called your advantage. And this advantage can be either positive or negative. A positive advantage means that we're going in the right direction and our policy model will be updated to further encourage that positive behavior, and vice versa for negative. So the DeepSeek team took this entire PPO algorithm and realized a few things. The first is that it's a little bit inefficient since you have to maintain a whole extra value model, which tends to be almost as large as the regular policy model on top of everything else needed for the reinforcement learning. Additionally, for things like teaching math and reasoning to language models, you're mostly going to be concerned with the accuracy of the final answer, not necessarily the intermediate steps. The value model helps out a lot when you care more about those intermediate steps, but not so much when you can just check the final answer against some ground truth. Which brings us then to group relative policy optimization, the modified version of PPO that the DeepSeek team implemented. So for a given training example, a question will first be input into the policy model, and then this is where the first change comes in. Multiple outputs are going to be generated from that policy model. So we're going to take some n sample size of outputs given the exact same input question. For each one of those outputs then, we're still going to be using the reference and reward model to calculate a final reward for each one of the outputs. Looking at all of the rewards from all of the outputs, we can find what the average reward is and then calculate our advantages a little bit differently, because now instead our advantage is going to be calculated based on how different the individual rewards are from the mean average reward. The policy is then updated based on the relative ranking of the outputs rather than a whole reward value. And the beauty of this is that GRPO then cares more about how well a response actually did compared to other responses for the same prompt, rather than trying to learn these absolute reward values. We'll get into exactly how this helped actually unlock emergent reasoning capabilities in a second, but one of the big benefits of this is that removing the value model and using this group relative scoring, it makes the reinforcement learning training process much more efficient, while also maintaining the alignment with human feedback. So this is really the core of why the DeepSeek team claims that they're able to push this incredible performance on limited hardware. And while the theoretical behind these reinforcement learning algorithms are cool to know, it's especially cool to see how they're actually applied. So let's take a turn now and look at how the team actually used GRPO to teach a language model to reason. The really neat part behind GRPO for reasoning is really that it allowed LLMs to learn to think naturally through problems longer without actually explicitly defining any functions that encourage this reasoning or thinking length. This was discovered with the creation of DeepSeek-R1-Zero, which is the predecessor to the now powerful R1. Essentially what they did is they took their base model, DeepSeek v3, as their candidate policy model for optimization. They then format all of their training examples with the below prompt template. That is a conversation between user and assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in the mind and then provides the user with the answer. The reasoning process and answers are enclosed within think XML tags and answer XML tags respectively. Most notably, in comparison to some of the speculative ways that we believed that reasoning was being taught to these models, this initial approach doesn't rely on any supervised fine-tuning to try and actually explicitly train a model on, reasoning examples or different reasoning processes. Rather, the reinforcement learning environment itself is meant to guide the language model to learn this behavior itself, which is kind of cool. The training data set in this case was primarily things with verifiable outcomes. They used a big mix of math, code, and logic-based questions, as especially for something like this, they're much more easily verifiable. Having a ground truth answer with something like a math problem or whatnot makes it really easy to do some reward modeling among the RL process. So after kicking off this training, they noticed a lot of really cool behaviors start to come out from the language model. Few surprising observations included the behavior of reflection. They now have the aha moment that they're calling it, where when a language model is actually thinking through and trying to solve a problem, it can reconsider what it did in the past to change its current steps. It also began to consider and explore different possible alternative methods for solving a problem, rather than just trying to solve it in one single pass or using zero-shot techniques. It also tended, as we see with this graph, to use more test time compute and generate longer chains of thoughts and longer answers as it reflects and explores different possibilities. It's really fascinating to see this because this essentially shows that the language model was naturally learning by itself to use more time and spend more time on these answers before actually submitting a final one. So just through pure reinforcement learning, a language model develops the ability to think longer and harder on a problem, which tended to give it much better outputs and much more accurate outputs in the end. So with this initial success and showing that GRPO works, given the data set to instill some reasoning capabilities naturally into a language model, they started to use it in a more formalized training pipeline to create what we now know as DeepSeek-R1. The full R1 training pipeline followed a 4-step process. The first step actually started with just regular supervised fine-tuning on long chain of thoughts examples. They started with the same base model of DeepSeek v3 and ran through with supervised fine-tuning thousands of labeled reasoning examples. These examples were gathered from the DeepSeek-Zero model that they created up here, as well as from human annotators and different few-shot synthetic data generation techniques. But supervised fine-tuning itself doesn't necessarily instill the behavior, rather more imitate the style. And so that's when they apply the group relative policy optimization for reasoning. So after the SFT happens, an initial training run using GRPO on a reasoning-oriented dataset is used to enhance the model's reasoning capabilities. They're once again going to be using things like coding, math, science, and logic-based examples, as these are much more easily verifiable. So now that they have a general reasoning model to start, the issue that they had is we want to generalize this reasoning behavior on non-reasoning specific data. Things like writing, roleplay, factual question and answering, translation, and whatnot. So they use the existing checkpoint that has undergone the fine-tuning and GRPO fine-tuning to create some curated examples for general purpose reasoning tasks. These roughly 800,000 curated examples are then used to perform more supervised fine-tuning on the existing checkpoint. They claim in their paper that they did this for 2 epochs, or a total of 1.6 million training examples of fine-tuning. The hope of this is to take the already preconditioned and trained for logical and straightforward reasoning model and generalize its reasoning capabilities towards non-verifiable or more fuzzy examples. A final stage then of GRPO is ran once more. This time it's more for the human alignment and harmfulness and helpfulness type of training, where a combination of reasoning-specific rewards and human preference reward models are used with the GRPO, along with a mix of different training data to do the final polishes and finishing touches on the model, which became the powerful DeepSeek-R1. The final result of this, and as we've come to understand, is that really this group relative policy optimization proved to be a powerful foundation for training reasoning capabilities within language models. The different scoring and removing needs for value models made it super simple to train, as they only needed rules-based rewards for accuracy and different format validation, which we'll show when we implement it in a second, to get this initial reasoning results. A lot simpler than we kind of thought a few months ago. Adding in the different supervised fine-tuning steps made this process a lot more stable and efficient, as we've seen, and the result matched OpenAI's early checkpoint of O1's performance, but with significantly reduced compute requirements. The most notable part of this, however, is that this algorithm of GRPO really enabled a strong generalization of reasoning patterns from not just technical domains like math and coding, but to broader tasks. And this really suggests that group relative training may be very effective at actually teaching foundational reasoning capabilities to language models. So now with our understanding of group relative policy optimization, what we can do is actually use some of the latest language model training libraries that have implemented this algorithm to apply it ourselves. For this specific example, I'm not necessarily going to be applying the entire training pipeline of R1. I'll leave that up to the professionals over at Hugging Face. Rather, what we're going to be doing is imitating sort of what was done with R1-Zero. More specifically, we're going to be using a small language model, Qwen 2.53b Instruct, and training it on GSM 8K math problems. This will create a small but mighty little math reasoning model that should hopefully learn to do a little bit more independent reasoning as it is ran through group relative policy optimization on these verifiable math problems. To do this, what I'm going to be doing is modifying a notebook that was originally created from Unsloth, a phenomenal piece of work from Daniel and Michael Han, who are specialists in really the algorithms behind optimizing and training these language models. So I'll have a bunch more resources related to Unsloth linked in the description below so that you can check out their stuff. But to walk through the code real quick, what we've got first here is just simply installing the dependencies. We're going to need Unsloth, VLLM for efficient inferencing, and then also a specific version of Transformers Reinforcement Learning, or TRL. This is a package that actually comes from Hugging Face that helps with doing reinforcement learning with language models. To start, we're going to be using a little bit of Unsloth magic to just patch up all of the code and make sure that it runs really efficiently. As you can see, I'm in a Google Colab environment here, and everything that I'm about to show you can be done using the base free GPU that comes with free access to a Colab notebook. So super cool work that enables this. Once again, the Unsloth team is phenomenal. But after running their GRPO specific patch and seeing that it will patch our computer to enable 2 times faster free fine tuning, what we can do is load and prepare our base model. As mentioned, we're going to be using Qwen 2.53b Instruct, which is just a nice, small, but powerful language model that would be a good candidate for our use case. So using the fast language model class with the method from pre-trained imported from Unsloth, what we can do is path over to the Hugging Face ID for 2.53b Instruct and implement a few different arguments, specifically the max sequence length, which is going to be the maximum amount of tokens that this language model is going to be able to actually generate. We're going to load it in 4-bit, which is going to be more of a parameter efficient way of loading this. We're going to use VLLM for fast inference. And then we're also going to be using LoRa adapters, or low rank adaptation matrices. Essentially what this means is that we're going to be training just a small part of the model, but it's going to be enough to actually alter and change the behavior of the model itself. Well, we're only going to be updating a small amount of weights. This is still going to be effective, and later we're going to merge those back into the base language model to create our full fine-tuned model. As such, what we need to do is prep the model for parameter efficient fine-tuning, which is what doing LoRa fine-tuning is going to do. We're going to specify a rank of 64. Essentially, a smaller rank is easier and faster to train, but doesn't capture as much of the complexities in its weighting as a higher rank does, because it's able to store more of those values and parameters to be fine-tuned. For this, I just used a rank of 64. We then attach what target modules we want to attach these extra LoRa adapters to train, and these are just going to be internal parts of the language model architecture. It's been found that with a LoRa adapter, attaching them to these specific parts of the language model are the best and most efficient way to do this kind of training. But with that, we've loaded the language model as well as the tokenizer and prepared it for parameter efficient fine-tuning. So it will now expect to have a LoRa adapter on it and be trainable with this method. Now with the model downloaded, set up, and loaded, what we can do is prepare our dataset. As mentioned, we're going to be using GSM 8K, which is 8,000 examples of grade school math problems. This is very much in line with how the original training of something like DeepSeek-R1-Zero worked, because they just used very verifiable examples in their dataset like logic problems, coding problems, and math problems. To simplify things, we're just going to be using math problems from this dataset. As a note, a lot of the data prep and reward functions that we're going to see is coming from this lovely man, Will CCBB's demonstration here. So while this is being repurposed for our use case, I'll leave his work in the comments below so that you can see the specifics of how it was implemented. Additionally, we're going to provide our own prompt template to encourage, but not necessarily teach the model to reason, and it's going to look a little bit like this. Literally just says, respond in the following format, reasoning, ... end reasoning, answer, ... end answer. So with our prompt and our format that we want, what we can do is go through, actually load the data set, split it into the train, and then prepare the data set into all of these exact nice formats, which in our case is going to be taking the original question as well as the answer, formatting the system prompt, adding in the question, and then extracting out just the specific answer. What we're going to be doing is encouraging the language model to do all of its reasoning through the problem in the reasoning tags and then just submit its final answer. So as you can see, all of these examples have these 4 hashtags and then a number, and we're just going to be simply extracting out that answer through this so that we can verify from the language model's output and its answer XML tags whether or not it is exact to our training example. So with our properly formatted data set and answers ready to go, what we can do is define our reward functions. As mentioned prior, the reward functions are going to kind of define how well the model's output is actually being scored or performing. And then of course, through training, the language model is going to work towards trying to maximize this score. And also, while reward models are a thing and training reward models and for something like human alignment is possible, the beauty of GRPO is that we don't actually need anything super duper fancy. The most important reward function that we're going to look at and define is actually just a correctness reward function, which is essentially just going to take the question, extract out the answer, and then determine whether or not the answer is exactly the same as the answer that we expect to see from our data set. The rest of these reward functions are simply going to be looking at the format that the language model is outputting in, making sure that it keeps just its thought process through the whole thing in the thinking tags, and then putting everything else, just the final answer, into the answer tags. And surprisingly, this is simply all that you need to actually kick off and start the model to learn how to reason on its own. We don't need anything that's super fancy for actually trying to encourage or reward reasoning, which could be prone to things like reward hacking, where the model's not necessarily actually learning the behavior, rather just maximizing the reward values. So very simply, with our correctness functions and a couple functions for checking out the formatting, we can encourage reasoning behavior and actually get the model up in training. So from the Transformer Reinforcement Learning package, we can create a GRPO config and a GRPO trainer. This config is nice and lengthy. I have some additional comments here for what each one of these arguments actually does, but the main thing we care about here is really the number of generations, which is going to be the number of responses that we generate per prompt for the GRPO algorithm. Also, the max completion length, which is going to be the maximum length of the model responses and tokens, and of course, the maximum steps that we take. From the GSM 8K dataset, it's roughly 8,000 examples, so for my model, I'm going to train on 2,000 of these examples. Packaging up the model, the tokenizer, all of our reward functions, our training arguments, and our data set together in a GRPO trainer, we can kick that off and start our training run. Hopping over to weights and biases to look at how the training run actually performed, we can see a few fun things here. We see that initially the model's just getting up and started, and then it has a decent time actually maintaining its reward for the first 500 steps. And then post 500 steps, it actually bumps up a little bit in its reward and starts to peak a little bit higher here. Of course, this is more of a small scale test on a smaller model, so we're not expecting any groundbreaking things here, but cool to see that our reinforcement learning is actually working. I've specifically uploaded this exact model to Hugging Face here, so you can check it out in a few different formats, both GGUF formats as well as just the LoRa and the raw floating point 16 version. But then over here, I have some instructions on how to actually run this once it's been saved. So once again, using unsloth to load our model, what we can do is go down here and prep our message. We'll use the classic how many R's are in the word strawberry, as well as our expected system prompt here, and create the text that we're going to pass to the model. So running that through. And then what we'll do is pass that all off to the model to process and output. And what we get back here is some reasoning. So we see to determine the number of R's in the word strawberry, we need to go through each letter of the word and count how many times. It says that it consists of 9 letters, the first R, the second R, and the third R. Does some good reasoning, and finally answers with just the number in the answer tags that it is 3. Putting in a more specific math problem with the sum of 3 consecutive integers is 1, 2, 3. What is the smallest of these integers? We can generate and see that it can also do a lot more math as well, correctly answering 40. So he's successfully been able to train a small model to learn and enhance a little bit of its reasoning capabilities with GRPO. In short, GRPO is a really cool and powerful method that came out of DeepSeek's research that is really unlocking the abilities to do these complex reasoning tasks in language models much more simply than we originally thought was possible. It's great to see as well that they've open sourced their entire methodology and training method, because this will definitely advance artificial intelligence in general with access to and understanding of all of these complex techniques. So after explaining GRPO and applying it ourselves to some models, I hope you learned a thing or two today and are excited to try applying this to your own specific domain. If you liked the video, consider giving the video a like. If you want to see more, definitely subscribe. And if you have any questions or comments, leave them in the comments below. I'll have further resources linked in the description. Thank you and have a great day.